So welcome. So last time we were talking about alternating current circuits, and the first thing we talked about was these AC sources and how they follow a sinusoidal curve, and how sometimes we represent them as a genuine sine curve and other times we represent them as a phasor diagram, and how both those things are useful. So this is a useful way of representing what happens during the cycle of a cycle of oscillation. We reviewed the fact that there's a problem in determining our average value. It's a time-varying current or a time-varying voltage, and so for things like power, we need to know some kind of average value of that. And yet, when we try to get the average of a symmetrically varying signal, we get zero. Could be +1, -1 volt, could be +1,000, -1,000 volts. It just gives you no idea of the size of it. So somehow we need to get an idea of the size of it. And traditionally the way you did that was you squared to get rid of the negative. It's the negative that's cancelling out the positive. So you square to get rid of the negative, then you do your averaging, and then you undo the squaring. So you square it, you average it, and then you root to get back from the squaring. And for some reason, rather than calling it the square root, rather than call it square root mean, we call it the root mean square. I don't know why, but that's what this is about, the root mean square. And basically, when you work it out because of the shape of the sine curve, then this comes out to be the average value. Well, I shouldn't really call it the average. The RMS value is 70% of the maximum value. So that's a useful thing just to remember. It's 70.71, who cares? 70% does it for me anyway. And so if I want to know the power dissipated when I put an AC signal through a resistor, I can simply use RMS values for voltage, RMS values for current, and it all works. So P is equal to IV as before, but now I'm using RMS values, whereas in the DC I use the steady value. So it works nicely. And then we started talking about resistors, capacitors, and inductors in a oscillating signal circuit, an AC circuit. And there were several points I wanted to get to. One was that we're used to the idea that when we have the maximum potential difference across a device, we get the maximum current flowing through it, because we're used to resistors. But ironically, because the capacitor and because the inductor don't work the same way, that intuition doesn't necessarily hold. And we talked about this last time about. So I can plot a graph of the current through the device versus the voltage across the device. And I'll see for a resistor that it is in phase. When we get the maximum of one, we get the maximum of the other. And if I take a point, and a point would be somewhere like here, if I take that time interval and plot it out, that's what I see where, yeah, the current's bigger than the voltage in this case on this scale, but they're both at the same angle. They're both at the same proportion through the cycle. And I can say, well, for this one, I equals V over R. And then I do the same thing for a inductor. There's the mathematics is shown here, and you can work your way through it. What I want you to get comfortable with is that we try to talk about the how the voltage pattern relates to the current pattern. What we see is if this is sine omega t, this is sine omega t minus 2 pi. Minus pi over 2, I'm sorry. So that means there's a phase difference between my current through my device and my voltage across the device. And I can plot it out here, and I can show this graph on an oscilloscope. That I find hard to really appreciate. This makes it much clearer. And so in this case, if I was to take a particular point in time, I would see that whereas this is in the first quadrant of the wave, this is actually way around here, almost at the end of the wave. So this other one is almost all the way around here. And that's how you get these two shapes. So, okay, there's a 90 degrees phase difference. and the inductor voltage is leading the current through the inductor. And then what I do is I say, well, hold on, how does my maximum current relate to the voltage? And I can get that from here and say, well, there's my voltage, and the maximum is when that equals 1. And what's this guy down here? Well, you know, I used to say that I is equal to V over R for a resistor, and this is I is equal to V over omega L. So by analogy, let's just say that this omega L acts like a resistor. I don't want to call it a resistor because it's not a resistor. It's an inductor, so I'll call it my impedance, my reactance. I'm sorry, I get those words mixed up all the time. Reactance. And it's given the symbol X. But it's got units of ohms. And what we see with that is that as I change my frequency, as I turn up the frequency of my AC, so the resistive character of my inductor gets more and more significant. So an inductor kills you at high frequencies. It puts a massive resistance into your circuit, reduces your current, which is like your signal, to very little value. So this is a low-pass filter at low frequencies. When that's a low number, that's a low number, and I get that as a low number, so I get a big current. So inductors, an L is a low-pass filter. It's going to let things that are near DC through without messing with them, but high frequency is going to kill you on. So then when I do the same kind of analysis for my capacitor, again, I find this graph looks rather like the previous graph, but it turns out if I take a situation like this, there's my time interval, then I see that my voltage has only gone around there a bit, whereas my current's gone around there a lot more. And I see it much easier in this phasor diagram than I do in this graph. So phasor diagrams are very useful. They are. I know it's something new, but they're really, nothing's added just to fill up space. It's like everything is added because it earns its keep. And phasor diagrams can really help you out in situation. And then again, I'm looking at how for my voltage, I have a sine omega t, and for my current, I have a sine omega t plus pi by 2. So this is 90 degrees ahead. The current is 90 degrees ahead of the voltage in this case. Okay, so again, I can do this thing where I say, well, my current is equal to, well, this times, well, before we had my current is equal to delta V over R. So this R is kind of like 1 over omega C. So we say, we'll call this our reactance, our capacitive reactance, which is 1 over omega C. And this kills you at low frequencies, because 1 over that means it goes like that. This is omega, and this is my reactance, or my resistance, if you like. And so the capacitor is killing you at low frequencies. So the inductor kills you at high frequencies, the capacitor kills you at low frequencies. So if you have a circuit with a resistor, a capacitor, and an inductor in it, then, man, you're going to be squeezed at the high frequencies and squeezed at the low frequencies. But there's a sweet spot in the middle where you get the minimum reactance, the minimum impedance, I'll call it, which is basically the overall effect of reactances. Minimum resistance in ohms. And so I get my maximum current through, which is my maximum signal. And so here we go to this classic, and I call it an LRC circuit because that's the phase angle order. So why not just learn it with that nomenclature so you always know the order with which the phases go. And so I have an LRC network, and they're in series, and basically what we know about series is the current flow at all points is the same. The potential differences can play around. So, okay, so I can recognize that my voltage is equal to my maximum current times R. My voltage across the inductor is maximum current times L. my voltage across the capacitor maximum current times XL XC. But there's a phase effect. There's an angular effect in time. So I got to express this more clearly. So my instantaneous voltage across my resistor is my maximum current modulated by the sine omega t. And when I take my voltage drop across my inductor, then yeah, it's my maximum current times my reactance, but it's modulated by the sine omega t plus pi over 2. And I get this guy for my capacitor, and again, it's the maximum current times my reactance for my capacitor, modified by the sine omega t minus pi over 2. There's a plus pi over 2, which is added 90 degrees. There's a minus pi over 2, which is subtracted 90 degrees. And what I know is that my voltage at any given instant is equal to my voltage across my resistor plus my voltage across the inductor plus my voltage across the capacitor, but that I have to add these vectorially, or as the phase diagram tells me to add them. And so I get this new treatment, which is a little bit different, which is basically, let's keep the currents all the same, because the current is the same, and then let's recognize that my voltage drop across my resistor is always in phase with my current. My voltage drop across my inductor is always 90 degrees ahead of the current, and my voltage drop across the capacitor is always 90 degrees behind my current. And these two voltage drops fight each other. You know, it's not 6 and 6 or 3 and 9. 9's going one way, 3's going the other. They're basically subtracting from each other. And that's not obvious unless you think about those phase angles. Well, what I find, for the way I analyze these circuits, is I find it actually most beneficial, not so much to think about this voltage graph, but to think about the equivalent resistance graph. And this is like the finished product, so I want to show you what's going on here. Looking at this diagram over here, I see that, well, my resistor would be, if I imagine my resistor like that horizontally, and if I imagine my XL is always in front and my XC is always behind, then I can add these guys vectorially. Well, this is a downwards and this is upwards, so that gives me my answer of that. This is XL minus XC. And then I have my resistance. And so I have this overall net resistivity, or resistance, I'm sorry. And I call that my impedance. And we give it the symbol Z. Whatever. And I have this phase angle. And that's where my impedance is with respect to my resistor. And so I can say my impedance is defined as, that means defined as, well, Pythagoras, the square root of r squared plus the difference between these two, XL minus XC squared. And then I can say, well, my maximum voltage is equal to my current times my impedance. And I can say that the phase angle is 10 to the minus 1 of the opposite over the adjacent. The opposite is XL minus XC, and the adjacent is it's R. I just want to see for a minute. Okay. I'm going to jump out here for a second. Oh, sorry. It's going to have me to discard it. I'm going to have to discard it, so I'm going to discard it. Okay, no big deal. I'm going to come in here, and I am going to, in here, I'm going to, let's have a look. I want to insert page. I'm in the wrong place, aren't I? New slide, new slide, new slide. And then let's go back here, go from the beginning, and then let's work our way down. So this is a typical problem. Okay, and I'm going to mess up on the numbers, but we'll figure it out. So that's going to go there. I have my AC. Inductor. Looks like a coil, doesn't it? Resistor. Capacitor. And I'm just going to I'm going to pick out some numbers. So let's have a look. I'm going to have that as 4 Henry. I'm going to have that as 3 ohms. I'm going to have this, I'm going to make this 2 times 10 to the minus 3 farads. This is my L, my R, and my C. And what I skipped over this time is, what is the resonant frequency? If this is resistance, I should really say ohms, because it's in resistance or reactance, and this here is frequency. And if the inductor is killing you at high frequencies and the capacitor is killing you at low frequencies, and the resistor is just constant, what we get is a situation where when I add these guys together, I get something that looks like that. I get my Z is that, the total effect. And as you see here, there's a minimum Z, Z min. When I have the frequency for my Z min, I get a maximum current, a maximum signal. And I call this omega naught, the resonant frequency. And it's got mechanical equivalence. Do you remember the trolley where the student waved the trolley backwards and forwards when we did oscillations and waves? And if she oscillated it at low frequency, the low frequency one oscillated most, and the others were still moving, but they didn't oscillate much. And then when she went to a higher frequency, the middle one oscillated most. And then when she went to the highest frequency, the third one oscillated most. So different ones picked up the energy at different frequencies. And that's resonance, basically, when the driving frequency matches the natural frequency of the system, then you tend to store more energy. And that's what's going on here. You have a radio station which is driving at too low a frequency. And so my radio set, which has this natural frequency, ignores it. I get killed by the impedance. It's like I received the signal, but the current is so low for my circuit at that frequency that I don't do really anything with it. And if I go to a frequency that's above my natural frequency, I still receive that input, but the current that it generates within me is so small at that frequency that it doesn't do much for me. And if I go to the natural frequency, although there is some resistance, it's the lowest resistance possible for this circuit. It's equal to the resistor's resistance. And so I get my maximum current flow, which means that my speaker gets enough energy to actually make sounds that go into the room. So it's almost like your speaker is trying to give you all the sounds from all the radio stations, but it only gives the biggest amplitude to the ones that are at its natural frequency, and the frequencies that are off to one side, you don't hear much of. And if you buy a more expensive stereo radio system, you get more definition. Your peak of acceptance is narrower. And so you can ignore those stations that are relatively close by and relatively close in frequency, but are not precisely the frequency that you want. So that's the game we're playing. So if I look at this impedance then what I would see is that I'm going to get a maximum current at the frequency where my driving frequency matches my natural frequency. So what does my natural frequency depend on? My natural frequency is equal to, what's it going to be? It's going to be the square root of LC, I think, if my memory serves me correctly. Am I right? No. Oh, 1 over. Yeah, I'm almost right. Good, thank you. So in this case, I can say my natural frequency is equal to 1 over the square root of L, which is 4, and my C, which is 2 times 10 to the minus 3, which equals 1 over 8 times 10 to the minus 3. And now the square root, I'm sorry, of 8 times 10 to the minus 3. So now I need my calculator, which I happen to have in my pocket. So that is going to be second square root 8 second EE minus 3 and inverse of that. Inverse 11.18. Now, what units do I have? The clue is in the symbols. It's going to be radians per second. Just for a laugh, let's just remind ourselves, omega equals 2 pi f. Yeah? So what is this? What is f naught? Is equal to omega naught over 2 pi, which equals 11.18 over 2 pi, which equals 11.18 divided by 2 enter divided by pi enter 1.78 hertz. This is not high frequency. Yep. Just check my numbers on that, but I think I'm right. 17.5. No, it's 11 over about 6. So I know it's going to be about 2. I'm wrong. Hold on. 11 divided by 2 enter divided by pi enter. No, I'm getting 1.7. Yeah, am I right? Yeah, I'm right. Okay, cool. Okay. That's a bit of a side. I can make it a bit more interesting by talking to you in terms of hertz, but knowing all the time you have to use radians per second in the equations, you know. Okay. So that's one thing I can do. The next thing I do is I deliberately take you to a frequency that is nearby. So I could say find XL at, and let's call it not 11 radians per second, let's say 13 radians per second. So you'd have to be able to recall then that XL is equal to omega L. And I kind of remember that by the graph. I remember that my inductor gives me a straight line. So this is going to equal omega, which is in this case 13, I defined that, times L, and L in this case is 4, which equals 52 what? 52, what's the units? Ohms. Okay. In addition, or alternatively, I could ask you to find me omega C, which equals 1 over omega C. Yeah, I remember that it's the inverse thing, which equals 1 over 13 times my C, which is 2 times 10 to the minus 3, which equals 1 over 26 times 10 to the minus 3, which equals 1 divided by 26 second EE minus 3, which equals 38 ohms. Next, find Z at 13 radians per second. So here in my diagram, and I need 52 ohms because that's my XL. I need 38 ohms because that's my XC. And I have 3 ohms. Can I make that, will you let me cheat a little bit? I want to make that 30. Just so that my angle works out, not been 90 degrees. So I'll change my resistance to 30 ohms. Okay? So I can visualize this, I can draw this like that, and I can say, oh look, this here is going to be 52 minus 38, which equals 2 makes 40, 14 ohms. And this here is 30 ohms. So then I say, well, Z, that's my Z, is equal to the square root, square of the hypotenuse, R squared plus XL minus XC squared. Z is equal to 30 squared plus 14 squared, square root of it, which equals, so I'm going to say 30 squared, enter, plus parentheses 14 squared, close parentheses, enter. That's 1096 seconds, square root, second answer. 33.1. Call it 33. Okay. Man, I think I changed that too much, but never mind, okay. So, I've gone the other way now. So then the next thing that I would do is I would say, what is my phi? And my phi is that angle there. And phi is equal to tan to the minus 1 of my rise, my opposite, which is 14, over my adjacent, which is 30, which equals second. Oh, so now what do I want my answer in? It's up to me. But I've got to know what I'm putting my answer in. So I look at my calculator, mine says it's in degrees, and that's okay, provided I write my answer in degrees, because I'm just stating an angle. If I was trying to use the angle, I might need to be more careful, but I've got to be careful about what it is and give it the right units. So I'm going to leave it in degrees. I'm okay with that. And I'm going to say second tangent to minus 1, 14 divided by 30. That's going to be 25 degrees. I'm just going to go back because there's just something that's just, I'm surprised that it's only 33 ohms for Z, so I'm just going to check that calculation again. So that's going to be 900 plus, that's going to be 14 times 14. Yeah, I guess maybe I'm right. It's just in my visualization, I keep thinking it's going to be a bigger number than that. Okay. So That's basically the pattern. I can pretty well assure you that something like that will be on the test. Yes?
So L is always going to be over C, or like on the graph?
L is always going to be on the... Oh, yes. So, because of that work we did here we found out, if you look at, don't look at the current. So this is how the textbook does it. It focuses on the voltage and it says, look how the current's varied. But later on we say the current is the same through all the devices. So I wish it had done it the other way. But if you look at this, when you're doing the inductor, the voltage is leading the current by 90. And when you're doing the inductor, the voltage is behind the current by 90. So later on, we say, oh, over here, I'm saying, well, the voltage will be in front by 90 for the inductor. The voltage will be behind by 90 for the capacitor. And so when I come over here, my impedance, my reactance for the inductor will always be up front, and my reactance for the capacitor will always be behind. So it's always going to have that pattern. It might be that XL is smaller than XC. If you think about it, in my example, I went to a frequency. I deliberately picked a frequency which was higher than my resonant frequency. So that means that I'm going to get a bigger reactance for the inductor because I'm higher. And so that's what I found. My reactance for the inductor was 52. My reactance for my capacitor is 38. I could have chosen a frequency below, in which case the reactance for my inductor would have been less than my reactance for my capacitor. And so my phase angle would have been the other way. I would still have had this diagram. It's still going to be that same order. But this one would be a longer arrow and that would be a shorter arrow. So that's why I remember LRC. It's just then you need never worry about the order. You know the order. Okay? So that's the skill, basically. Expect that. Expect something like that. The numbers will not be the same. I might not ask you for every step, but I could ask you it for in hertz. I could say, oh, let's go do 65 hertz. And you've got to know, oh, I can't put 65 into these omega L equations. If I put that, it's going to be completely wrong. So you've got to figure it out. Cool. Next thing, power. So we said, okay, power equals volts times amps. Okay, as long as we're in AC, then we need, so power is equal to volts times amps, and as long as I'm RMS and RMS, I'm fine. And then we say, well, hold on. What we can say is, I'm just trying to cut to the chase on this. Oh yeah, I can say V is equal to IR. So I can substitute in this for V, and that would be IR times I. And as long as that's RMS, and that's RMS, then that gives me I squared R, but that has to be in RMS. So my advice is, whenever you're in AC, work in RMS unless I'm definitely asking you for the maximum. If I plot out the current that I get at different frequencies. So here what's happened is someone's done that calculation we just did for a whole bunch of different frequencies. They put it in Excel, basically. And what they found was as the resistance got smaller and smaller, so they got a higher and higher current flowing. And in the end, the current was limited by, well, the minimum value for the impedance. And the minimum value for the impedance is when those two cancel each other out. They're not zero, they just got a balance. And then my resistor is R. And so that's when you're at your resonant frequency, your impedance equals your resistance. Okay? It turns out that the smaller the resistor, the bigger the current, and so you get a sharper peak. So ideally, when I'm doing my LRC circuit, I want R to be kind of small. Okay. Well, I'm going to maybe modify that in a minute, but kind of small. So, okay. So I see where these three graphs come from. We're going to do a lab next time where we use our circuit, and ours is not nice like this. If you think about it, if that's a linear expression, if this is ohms and this is radians per second, if that's linear and that's inverse, this is not going to be a nicely symmetrical resistance. It's going to be asymmetrical, if you like. I can't draw it. I can draw it, but it's going to be more like that, say. Just because this is linear and that's inverse, they're not mirror images of each other. If they're not mirror images of each other, then neither is this going to be. And so that means that in our experiment, we're not going to get that. We're going to get something that's much more, well, we're going to plot this, but we're going to get something that's much more like that. So clearly they're using a nice system here. And what they're probably using, well, it could be that they're only looking at a very narrow range. So you don't see the asymmetry. That might be partly what they're doing. Or they could be using a different type of circuit. We're using the most principled circuit, where the analysis is accessible to us. But they have what they call tank circuits, where they basically, the one I saw one where they had the inductor, and I think it was in parallel with the capacitor, and then they had the resistor coming off it, something like that. And they can play games like that. So when you buy, if you go and buy a Bang & Olufsen receiver, it does not have three components inside it, you know. It's got a lot more sophistication than that. Okay, so it'd be nice if we could characterize how sharp this peak is, and so we have this so-called power factor, which our quality factor, which is basically our value for our resonance divided by the full width at half max. Full width half max. And I remember my first job in industry, I was a spectroscopist working on a mass spectroscopy project, and we spoke all the time about FWHM, full width half max. It was like a very nice way of characterizing how sharp is your peak. You know. That's what they use. They say, okay, the quality factor will be the resonant, I'm sorry, I did it backwards round, didn't I? It's the resonant frequency over the full width at half max, which will give you a big number, which makes sense. Bigger the quality factor, the sharper the peak. That's a good way of remembering which way around it is. Okay? And because we know that we can substitute in, I guess, and we get this omega naught L over R. Oh yeah, so the smaller the R and the bigger the L, the better the quality factor. Okay. Cool. So, any questions on that so far? You kind of know where we're going? You know, can you work out the impedance for an inductor, for the reactance for an inductor? Can you work out the reactance for a capacitor? Can you work out the resonant frequency for a circuit? Can you work me out what the impedance is for the entire circuit? Can you work me out what the angle is? And could you work me out the quality factor? That kind of thing. Okay, that's where I'm going. I've not tended to ask much about quality factor in the past, but I feel like that's a bit lacking. You get in the habit of not asking for something, so. And then when you say, well, do I want to blindside them with this? So I'm warning you that I'm getting more likely to include the quality factor than 5 years ago. So you might not see it in many of the tests before, but I'm feeling more like asking it. No guarantees, but I'm feeling more like asking it. Every time I look at it, I think, man, I should focus a bit more on this. Next, and I think this is the last thing, yeah. This is, I think it's kind of out of sequence, but basically we did this mutual inductance. And the idea was that the changing magnetic field caused by an AC signal on one coil will cause a changing magnetic field that induces a changing magnetic field which causes a changing EMF on a second coil. In a way, it's brilliant. Okay. So that becomes the transformer. I think the transformer is... I didn't appreciate it when I was a student. It was just like another thing. But I think this is... An electrical engineer might correct me on this, but I think this is the crux for why AC beat DC in that battle of who's going to supply the electrical energy to the world. Because with this, by using a simple combination of two coils with different numbers of turns, I can change the characteristic of my energy. It's still the same amount of energy, still the same amount of energy per second flowing through this device. The power is the same. But I can have one current here and one voltage here and another current here and another voltage there. And as long as the products are constant, then everything's happy. Well, who cares? Well, this is why I care. If you think about it, we kind of just said, did I say it? Did I skip it or did I say it there? I said it down here, didn't I? Power equals I squared R. And I say it again there. Power equals I squared R. What does that mean? That means that basically your heating effect, power dissipated, your heating effect goes with the current. And the current squared. So if I have a choice between doubling my current or, so if I have a choice of, let's say, if I have a choice of 1 amp and 2 volts, so this is I and this is V, or 2 amps and 1 volt, this is I, this is V. These are the same power, agreed? 2 times 1 is 2. 1 times 2 is 2, yeah? Same power. Power equals IV, yeah? But the heating effect on this guy scales with the current squared. So the heating effect on this guy is 4 times heating effect than on this side. So, if I want to transfer energy to you over a long distance, I'm going to jack my voltage up as high as I can get it and send you next to no current. You still get all the energy. It's like having a high-pressure pneumatic system. I can still do work on you. I can still give you the energy. Not a lot of matter flows, not a lot of electrons flow, but hey, those electrons that do flow have a very high energy content. So it's... And then, all right, so you don't want to work with a high voltage. You just use another transformer to step down to a higher voltage, lower frequency. Lower voltage, higher current. And that's what we do in our power stations and in our grid. Power stations mix electrical energy, and then we use a transformer in the power station to make that electrical energy something like, I've seen, 360,000 volts, 700,000 volts, whatever. And then you ship it across the countryside. And when you drive down the interstate and you see those big power where they've actually cut all the trees away. No one lives underneath them. I mean, that tells you they take it seriously. That's a very high voltage system. And you can actually don't do this, but I've seen videos of people with neon tubes, like tubes like out of the fluorescent tubes, and you hold them up in the air, and because the electrical field is so strong, they will actually strike an arc, and they'll glow, not particularly well, but they'll glow in the dark, because the electric field is so different between one point and the other. You ship it like that, relatively small losses. Then when it gets to your subdivision, it goes through a substation, and it gets transferred down to maybe 400 volts with lots more current. And then it goes down your street, and it gets transferred to 120 volts with even more current. So that's the game they play. And it's all available via the transformer. So it's just a very nice device. And in principle, this is the same for the cordless toothbrush. You know, if you think about it, we've got AC on one coil and we've got another coil close by, and the energy gets transferred across. The difference is that with the cordless toothbrush, I'm not that worried about efficiency, so I don't worry about having a really good magnetic connection between the two. But with a transformer, I want a really good connection. So I actually get myself some laminated soft iron, and I basically make it, because what this will do is it will entrain the magnetic flux line, so that every flux line coming out of here goes in through there. So it makes it like they're magnetically really well coupled. The trade-off is it becomes quite heavy. So if you pick up a power supply, it will have a transformer inside, and that power supply weighs a lot. It's because of the metalwork in the transformers. Okay. So what we have is we have our voltage on the first coil is the number minus times the number of turns times d flux by dt, and on the second one it's minus the number of turns times the flux by dt. And if I remember that these two guys are equal to each other, so then I get delta V over N1 equals delta V over N2. And so that's my transformer equation. I like to remember it, frankly, as the ratio of the voltages is like the ratio of the turns. If you look at that, just rearrange that. If I take my N1 to the other side, it's the same equation. And I just remember a lot easier the ratio of the voltages, the ratio of the terms. Okay. Either way. And so I can simply put in a number, so I can say, oh, look, I'm going to give you an AC of 20 volts, and I'm going to give you 15 turns, and over here I'm going to give you 5 turns. So what's my AC voltage coming out? And you go, well, the ratio of the turns is 1 to 3, so the ratio of the voltages is 1 to 3. So this would be 1/3 of 20, which equals what is it, 6.6 volts. Let me just double check on that. The ratio of my voltages, 20 to that, is the ratio of my turns, yes. It's very nice. If I want, I can use V equals IR, and I can say, well, my current in my first times my potential difference on my first is equal to my current in my second. That's just saying the power equals the power. You don't get anything and you don't lose anything. Now you do lose. They're not 100% efficient. There's a lot of heating takes place, but they try and minimize it. Let me ask you something. Does the frequency matter? Not particularly. But no oscillation, no transformer. It's not a DC device. So I suspect, I've never checked this out, I suspect as you go to low frequencies, it starts getting less and less efficient. I don't believe it goes into, if you have a billionth of a hertz, then you go to 0, it stops, you know. I don't believe in sharp edges anymore. Okay. So as you go to lower and lower frequency, I suspect it gets less and less efficient. And that's it. I love transformers. So when I look at this section, there's 3 bits, isn't there? Can you tell me what a root mean square is? Can you do me my AC circuit? And can you tell me about a transformer? Those are my 3 bits for that. Oh, and now they are. They say they're ubiquitous. They're everywhere, and we've got them everywhere, so we don't even notice them anymore. It's like they're just everywhere. And if you notice, that's not a heavy thing. I mean, I don't know what the technology is in there, but it's they're just all over the place. By the way, as we're going to find out, I'm going to stop this because we don't need it anymore.